All right, so this is Module 23, and we're going to be looking at a topic that's similar to what we've been looking at with arrays with numeric values, but this time with character values inside of our arrays. And to some extent, this wouldn't need to be really a separate topic if it weren't for the fact that character arrays, or better known as strings of text, a word, are so common in programming that we've got some slightly different conventions for utilizing or using these arrays. And so there's a separate term for character arrays, typically called C strings, and that's the topic of this module. C strings are covered in depth in section 7.11 in the textbook. And just as a side note, the reason they're called C strings is to sort of differentiate between the older style C string of storing character arrays or working with strings of text, as opposed to a newer way, which now we just call strings, that has been introduced in C++. So in this module, we're looking at the older style C-string based approach, which is still used in many applications. It's still used in many situations. And then in the next module, we'll look at a newer approach, which requires us to understand a little bit more about C++'s notion of object-oriented programming. So let's start with the basics. What is an array of characters? Certainly an array of numbers normally represents sort of a list of data or a list of values. A list of characters, in fact, actually taking a step back, one of the first things that we learned in C++ was how to print things out and how to store literal values. And it might have been a little tricky the first time you thought about the difference between a string with double quotes and a single quote, single character. In the real world, in our everyday experiences, we don't really think about there being a difference between a single character and multiple characters, a word. But we quickly learn that there is a difference in in programming, in computer science. And we learn that we have a variable of type character, or char, that allows us to store a single character, but we didn't really necessarily have a data type that could store a sequence of characters, a string of characters. Now, since we've learned arrays, we certainly know, well, yeah, we certainly do. We just create a character array. And so what we have here is there is no native data type for strings, but we certainly can declare one, and we know all about, arrays, about partially filled arrays, and we can just represent it as an array with a count. And that's what we see over here. In a partially filled array, in a numeric partially filled array, we know that we always have to keep track of how many values are actually in the array. And that goes for practical reasons, right? So if we want to print out the entire array, that means we need to walk through each and every index where there's a valid number, and we need to print it out. We also have to remember, sort of how long the array is and whether we're past the bounds of the array and all that kind of stuff. Now, having that separate count variable, so if we go back to this last slide, having that separate count variable, we're used to seeing it with numbers, it does create a little bit of an inconvenience. And one of the inconvenient things about it is that we always have to pass an array with its count to any functions that accept that array as a parameter. It's almost impossible to think of a function that would accept an array as a parameter and not also accept the count of how many things that are in the array. So you're sort of left with this situation where you're constantly passing back and forth multiple variables to represent a single thing. You're representing a single list, but you have to pass along the array and a separate count. Strings are so common that we've invented our own little special convention for this. And so rather than storing a count externally in a separate variable, instead, the convention with character strings is to put a very special character right at the end of the array, and that's called the null character. The null character looks like two characters, but notice we've got a single quote here. The literal value has a single quote. It is only a single character, but it uses two keystrokes. That backslash is an escape sequence. You might have already seen /n for new line, /t for a tab character. There's several special characters in the ASCII character set that don't correspond to a single letter. They correspond to an escape character plus some other character. So this is a 0. So the null character, you can type it in. You can't type it in a keyboard, but there's no key corresponding to it. But if you type / and 0, that'll be the null character. That character is always placed as the last character in the string. Now, if you don't have room, of course, if I tried to say hello and then added, the character A and B, if I don't have room for the null character, I'm in trouble. I have to make sure that I put the null character at the end of my valid characters. If I do that, that is sort of, it tells everybody that that's the end of the character array, and that's the end of the string. What I want to stress is that this is really, it's just simply an alternative to storing the length as a separate variable. If we store the length as a separate variable, we sort of implicitly know if the length says 5, if count is 5, we know that index 5 over here, 0, 1, 2, 3, 4, 5, we know that index 5 is outside of the list of numbers or the list of characters. By putting the null character here, we're just saying this index 5, is outside that string. The advantage here is that when we send C strings to different functions, the information needed to know where that string stops is already in the array, and that's very advantageous. Now, one question might be, you might be thinking about it and say, why didn't we do this with numeric arrays? Putting a special number at the end of every single array would have prevented us from having to worry about that count problem in the first place. And that is somewhat true, but there's two arguments against that. One, it's very difficult to figure out a number that everybody can agree that would always mean the end of the number line or a number string. We could use -1, but then of course we couldn't store -1 in an array without misinterpreting it as the end of the array. The beauty of the null character is that it's never validly used. Its only purpose, it's a totally invented character. The only purpose to the null character is to mark the end of the string. There is no such number that's only purpose for existing is to mark the end of an array. So that's one reason. There's no good number. The other reason is a little bit more abstract, or a little bit, you have to take my word for it a little bit, in that most of the time we use numbers, we actually need to know the count. We need to know how many numbers we have in a list often. We need to incrementally add to the list, and to be able to incrementally add to the list, we need to know where the next element is. For strings, we tend not to incrementally add to the end of a string. A string usually represents a word, and the word is just sort of static, and once we set it, we don't really reuse it. We might change it entirely, but we don't typically append to the end of the string. And because of that, it's not nearly as useful to have that count stored externally, where it would be very useful to have count stored externally if you wanted to actually append to the end of the array. So it just turns out that it's more convenient for C strings to use this approach by putting a sentinel at the end rather than numerics, where it's usually much more convenient in practice to have a separate count variable. All right, so how do we read an array of numbers? Well, we have a do-while loop typically, and we ask the user to type in one number at a time. And we know how they type that in, right? They type 1 and then they hit enter, and they type 2 and they hit enter. And every time we hit enter, we have a cin statement that reads in a number and we place it into the array. If we ask the user to type in a word, we certainly don't want to read one character at a time. We don't want the user to type in hello by typing H, enter, E, enter, L, enter, and so on. We want the user to be able to just read in the whole line or to type in the whole line of text. So for that, we've got a special syntax, and for now we're going to talk about this as a special function called cin.getLine. And within the context of this module, we can really think about this dot as really just being any other character. What we'll learn in the next module is that this dot actually signifies that Cin is an object, and this is a whole object-oriented paradigm where this is not just a function, but it's a member function of a particular object. We don't need to worry about it too much right now. We can just think of Cin.getLine as an ordinary function. That function takes two parameters. It takes an array to store the string, a C string, and it takes the maximum size of that string. And Cin.getLine will automatically wait for the user to type in a whole bunch of characters and hit enter. And when I hit enter, Cin.getLine will take all the characters that the user's typed in. It'll place them into your character array and will automatically put that null character at the end. So after calling Cin.getLine, so you're not going to do Cin arrow arrow to get a C string. You're going to call Cin.getLine, and that's going to allow you to read in an entire string. And once that returns, you know that the null character is at the end of that string. Likewise, output is a bit easier with C strings. If we were going to print out a list of numbers that were stored in an array, we would typically use a for loop. For C strings, we don't have a count variable, so we would need to perhaps have a while loop. We need to say sort of like, we need to walk through each individual character and say, while I haven't found the null character, print out this character and go to the next element. And we could certainly do that, and we'll do a variant of that in a second. But printing, it's so common and really it's so straightforward that cout can actually just handle it itself. So luckily, as long as our character array has a null character at the end, and that's a very important caveat, because if it does not, if you just say cout with an array that has not been well formed with a null character, you're going to get a lot of garbage to print out. But if you have a proper C string, you can just feed that to Cin just as any other variable. So remember, a typical numeric array certainly could not be printed out like this. You'd need a loop. For a C string, cout has the capability of figuring out, because it can find that null character, it can print out your characters. So let's use this stuff in practice a bit. What I'm going to do is have an exercise where the user is going to type in two C strings, two independent C strings, and my program is going to print out whether or not they're equal. And I'll define equal as they're the same length and they have the same contents. And I'm going to be in particular about that, in that I'll make sure that they're the same length before I even bother checking the rest of the content within the string. Note, the double equal sign does not work with arrays of any kind. It didn't work with numeric arrays. It doesn't work with strings. So I'm going to create a function that takes two C strings and will return true or false whether or not they're equal to each other. So let's bring this up. And I've got the program started. And let's create two strings for the user to start to type in. So I'll just call them string 1, and I'll make a maximum of 50, character string 2, maximum of 50, and I'll start prompting. So please enter first string. And I'll use Cin.getLine to go get string 1. The maximum size is 50. And Cin.getLine will make sure if the user types in 100 characters, it'll only give you the first 49. And then in the 50th element, the element number 49, there'll be a null character. I'll go get the next string. And just for now, let's print them out and make sure it all works. We want to always, if we're using C strings, we want to include C string. Again, it's one of those include files like CMath that Visual Studio will often include automatically for you. But you want to make sure that you always include it yourself, because if somebody works with your code that's not using Visual Studio, your code won't compile. And that's never a good thing. So I'm just going to echo back out to the user just to sort of prove that it worked. Build this. Let's give this a run. Okay, so we've confirmed that we can read in two strings and just print them out. Notice you never see the null character, but it is indeed there. So now let's create a function. Let's say equal. That takes two character arrays. Character array A, character array B. And it's going to return true or false based on whether or not those character arrays are equal. For now, in a kind of a top-down approach, I'm just going to return false. We'll go down here in our main program, and I'll say if equal string 1, string 2, these strings are equal. Else, these strings are different. All right, so that function eventually is going to have to walk through and check whether these are different. If I run the program now, of course, it doesn't matter what I type in, I'm still going to have the strings are different because my function always returns false. Okay, so how do we determine whether a string is equal? If not the same length, we'll return false. All right, so we'll have to figure out, how do we figure out the length of the string? And then also, if they are the same length, check each element, and if any elements don't match, return false. And then if I get past all that, I'll just return true. All right, so how do we find out whether two strings are of the same length? And this is an interesting point, because if these were numeric arrays, this would be really trivial, because if they were numeric arrays, we'd probably have a count variable associated with A, maybe count A, and we'd have a count variable associated with B, perhaps count B. Since we don't, we need to actually look inside of A and look inside of B and find where the null character is. And once we find where the null character is, if we find a null character at element 5, then we know that the length of the string is 5. So I'm going to build another function, length. And I'm going to take a single character string, and I'm going to find the length. And with this, I'm just going to write this right now. I'm going to walk through using a while loop, by the way, not a for loop, because I don't know ahead of time how many times my loop's going to go around. So I'm going to write a while loop that walks through starting at index 0, that keeps going until it finds the null character. So while string I is not equal to the null character, remember single quotes, I++. So all this loop does is start at element 0, checks to see whether it's null. If it is not null, moves to element 1, checks to see whether element 1 is it. At the end of this loop, I can return I, and that'll be my length. So if I say if length A is not equal to length B, return false. Now, for each element, I can do a kind of a similar loop as this. So let me make these a little bit smaller here so they fit on the screen. I can say int I equals 0, while, and now since I know they're the same length, I really don't care whether I'm checking A or B in terms of when to stop, because I know that they're going to stop at the same location. If they didn't stop at the same location, I would have returned false already. So I'll say while I is not equal to the null character. Yes, I'm going to do I++ eventually. Again, you could write this as a for loop. It would be kind of awkward. And by the way, it would not be a do-while loop because it's not a pre-test loop. It's not a post-test loop. We're not guaranteed to go around at least one time because it's very possible that this string could be empty and not have any characters. The null character could be at the first location. Or a mismatch could be at the first location in this case. So I'm going to say if AI is not equal to BI, return false. If I find characters that don't match, return false right away. If they do match, I'm not going to return true. I'm just going to move on to the next character. Keep going forward. Let's give this a build. Certainly those should be different. ABC, ABC, those are equal. ABC, ABCD, those are different. ACB, ACE, I think we get the point. All right, so this looks to be working correctly. So we see some common themes here I want to point out. Whenever we're processing a character string, whether we're processing it just simply to find out the length, or we're processing it to see whether it mismatches, or we're processing it for any other reason, we could be going through and turning the whole string into uppercase or lowercase. Generally, it's always a pre-test regular while loop. We always start at index 0. We always keep going around until we find the null character, and we always make sure that we move to the right each time. It's very similar to a for loop structure, but this part isn't simply, I less than something. It's really a condition, and that's why it's more natural as a while loop. Sometimes you will see people write it this way: for int I equals 0, a I not equal to the null character, I++, and then do something. And that's okay too. There's nothing technically wrong with that. Even though it is a little bit shorter, I tend not to like it. I find that this is a little bit more readable, and it jumps out to me that it's a character string where this starts to look a little bit different. But we're certainly seeing these common themes, right? Whenever we're processing a C string, we're going through with a while loop. All right, so let's keep going. The C string library, it actually provides more than just C and .getLine. And you might have imagined that finding the length of a string or comparing two strings to each other is a pretty common application. It's a pretty common operation that we're going to want to do. And because of that, the C string library, in fact, already includes some functions to do what we just did ourselves. So there's nothing wrong with doing things yourself, but if there's a library function, you might as well learn it. We can find the length of a string by calling string length, strlen, and pass that a C string, and it'll return the length. Very, very similar to what we already had. In fact, I can go over into my code here and completely remove length, and instead call string length. And it's pretty much a complete drop-in. It's something that's included already in C string, and we can utilize it. It's written exactly the way we wrote ours. There's really no difference between the two. And if I run this, it's going to be the same thing. ABCD. And that's perfectly fine. We can take it a step further, though. There's a function called string compare, which takes two character strings, just like our equal function. However, it doesn't return Boolean. And this is a little bit confusing the first time you see it. Instead of returning true or false, the string compare function isn't simply checking whether they're the same. It's trying to determine how they compare against each other in a dictionary. And it's a very common style of writing a function. So if string 1 comes before string 2 in the dictionary, otherwise meaning string 1 is less than string 2, it'll return a -1 or a negative number. If string 2 is before string 1 in the dictionary, it'll return a positive number. Otherwise, if they are equal, it returns 0. So it takes some time to remember that. It takes some time to get used to that. But once we know that, if we want to compare and check to see whether the two strings are equal to each other, it's a matter of calling string compare and seeing whether string compare returns 0. Rather than saying if equal, we say the string compare returns 0. We could, in fact, just replace this by entirely. Take the whole thing out. And down here, and actually I'll get rid of it. And down here we can call string length. If string length is equal to 0, then they're equal, and if they're not, then they're different. Oops. So we've got our string compare function. And what we'll see is, of course, it works perfectly fine. If we don't like the fact that string compare returns 0 when they're equal, we could actually write a wrapper function called equal. Basically the same thing I had before, and I'll just paste it back in here. And I can say if string compare a, b is equal to 0, return true, else return false. And now, if I write this at the top of my program and I have to do a lot of comparison checking, it might pay off because now I've got a little bit of an easier function to call. Whether that's really worth it is pretty debatable, whether you want to write a wrapper function or not. It's certainly not required. By the way, you could also do this. Return whether or not this expression is true. Either way is fine. Again, I probably would just use string compare right off the bat without the wrapper. There are more character functions also in the C string or the character processing libraries of C++. So there's another library called cctype. Doesn't actually deal with strings per se, but it deals with characters. And it's got some really useful functions that will tell us whether a particular character is of a certain type or convert characters into different types. So is upper, is lower will return 1 if C is uppercase or lowercase, if the input parameter is uppercase or lowercase. Is alpha will return 1 if the character you give it is A through Z, capital or lowercase or capitalized. Is space returns 1 if C is a space character, and that means a space bar, a tab, a new line, a carriage return, any type of blank space. To upper and to lower are for converting. So if you give the lowercase e to upper, it'll return uppercase e. And if you give uppercase e to upper, it'll still return uppercase e. So you can pass in any type of a character and it'll always return a capitalized version. Then if you call to upper with a semicolon, it'll just return a semicolon. And to lower works pretty much the same way. So these functions are all found in this cctype library, and they actually are quite useful. They come in handy a lot. All right, so on to the next example. Programming example, or exercise 34. We're going to test whether or not a given string is a palindrome. And a palindrome is a string that reads the same backwards and forwards. So I'm going to read a single C string from the user and then basically just print out yes or no whether or not they're a palindrome. And I'm going to throw in a couple of curveballs here. Not only is the standard string going to be examined, but I also want to kind of ignore the impact of uppercase and lowercase. So A, B, capital A is still a palindrome. I also want to ignore spaces. So A space B A would be considered a palindrome. Now those two bullet points are essentially going to require me to clean the input. I'm going to take input from the user that might contain capitalized letters, it might contain spaces, and eventually what I'm going to do is I'm going to check to see whether some version of the input is clean, is a palindrome, and that version is going to be, I call it cleaned up input, but really what it is it's the input with all the letters converted either to uppercase or lowercase, so there's no mismatches, and all the spaces removed. Now that being said, that's not where I'm going to start. I'm actually going to look at these two bullet points and realize, you know what, these are special cases. I need to first decide whether or not a string, given everything's lowercase and no spaces, I need to be able to determine whether it's a palindrome or not. That's the heart of this problem. And then we can figure out how to deal with the capitalized versions and spaces later. This is an exercise that if you try to start by handling the uppercase, lowercase, and the spaces within the same code that you're trying to figure out whether it's a palindrome or not, you could take a long time to finish this program. So the order in which I'm going to do this program is really critical. I'm going to first decide how to figure out whether a basic, all lowercase, no space string is a palindrome. Once I get that function to work correctly, then I'm simply going to make sure that I always call that function uncleaned input that doesn't have capitalized or spaces. And that'll make this process a lot easier to handle. Okay, so I have I switched over here to Visual Studio, and I have a program that it doesn't do any of the new stuff here. It just has a stub for is palindrome, but it's just got the basic setup. I'm going to remove this. We'll see that in a couple seconds. Let me switch this back. This is where I want to start the program, and all I'm doing is I'm creating a C string. I'm reading it in using cin.getLine. I'm calling this function is palindrome, which I haven't created yet, and just print out palindrome or not. So I've got the top-down approach. I've got the first part of it already written. And if I run this, P34, whoops, let's see here. If I run this, ABC, of course it comes out with no. Because it's not a palindrome, because I'm returning false. Right, so let's start and let's try to figure out how we take an arbitrary string, and I'm going to also say up here there's an assumption. All lowercase, no spaces. Right? That's the assumption. S is all lowercases containing no spaces. So let's figure out how we could write this function. I'm going to start out by kind of drawing a strategy for this. So let's assume we've got a C string, and let's say we've got A, B, C, C, B, A, and also I should add a little bit here. We've got a null character at the end. We've got indexes, right? So we've got 0, 1, 2, 3, 4, 5. How are we going to determine whether this is a palindrome? The easiest way to do this would be to have actually two positional counters. So let's mark one with one color. Let's start at 0. Let's call this I. And let's take another one and let's start it at the end. Let's call it J. In order for this string to be a palindrome, at every given moment, J is going to move this way, I is going to move this way. And every time I move these, I want to compare the characters. Right? So A is equal to A. Good. Then I look at the next pair. I will go forward, J will go backwards, and I compare these two with each other. Right? And I'm going to keep doing that. I'm going to stop switching colors here. I'm going to just draw in yellow. I'm going to keep doing that until eventually, and actually maybe it would make more sense to carry this forward, eventually I need to stop. Right? And I'm going to stop when I and J cross. Right? When J keeps moving left and starts looking here, and I starts moving right and starts looking over here, I know that I've examined all the pairs, right? And so I'll stop. Now, another option or another possibility, I don't need to draw all these squares here, is that I've got something like this, right? So an odd number of values. And if I had that situation, right, I'd have I and J. They would both move, and they would meet at a given location. So in both these circumstances, if I have two counters, starting at the end, starting at the beginning, moving towards each other, and now we start to think, well, how would I actually do this? Well, I'd write a while loop that every time around the while loop did an I++ and a J minus. And I compared the character at I and the character at J. I'm going to continue to keep doing I++ and J minus until one of these conditions occur. Either they cross or they meet. And what I can do is just say while I is less than J. While I is less than J, while I is to the left of J, keep comparing, keep moving. In this case, since they met, I would be equal to J, and my while loop would stop. So I'm going to design a single while loop that keeps track of an I and a J value and compares these two. If they're ever a mismatch, I'm going to return false. If they meet and while I less than J stops being true, then I know that I've reached every single pair and I can return true, that this is a palindrome. So let's implement that in our code. I'm going to have I start at 0. I'm going to have J start at the last index. Now, if we look at this, how do I get to the last index? Well, the length of this string would be a total of 6 characters, but the last index is 5. The length of this string would be a total of 3 characters, but the last index is 2. I can get the length of the string by calling string length, and then I just need to subtract 1. And I'll include C string for this. Now I've got my while loop. While I is less than J, if S at I is not equal to S at J, then I return false. It's not a palindrome. Otherwise, it's not returned true. It's just keep going. I++, J minus. If I get through the entire while loop, I either meets J or crosses over. Return true because I never found a mismatch. So let's build this and see if we've got this working. A, B, C, C, B, A, palindrome. A, B, A, palindrome. A, B, C, nope. A, B, C, A, nope. All right, looks good. Next, A, B, A, or A, B, lowercase a. That's not a palindrome. We want that to be a palindrome. A space BA, not a palindrome, but we want it to be a palindrome because we want to ignore capitalization and we want to ignore spaces. So what I've done is I've got my program to work based on a simple assumption. But now, what if some of these are spaces? Right? So there's two ways to attack this program. Right? One way is to now start messing with this function, to start changing is palindrome to make it more complicated, to figure out whether or not these things are the same case or not, to determine whether one of them is a space and maybe we ignore it. Or, as a second option, we still make sure that S has all lowercase and no spaces. And in order to make sure of that, we clean the input. Meaning we transform the input from the user to something that we know how to work with. Most times that turns out to be a much simpler solution. Transform the input into something you know how to deal with easily is usually a lot easier than changing your method to deal with all sorts of different complicated inputs. And don't forget that. That's a really good strategy to take on whenever you're trying to do some problem solving. So I'm gonna create a separate character string. I'll call it C. And what I'm going to do is write a function called clean that takes the raw input and takes an array. Maybe we'll call it cleaned in here, that it will put a transformed set of inputs into it. So when I call clean, I'll pass in the input and I'll give it my array. And now ultimately I'm going to check to see whether C is a palindrome. Right? So after calling clean, C, or cleaned, will contain all the same character as raw input has, but all characters would be lowercase. And if raw input had any spaces, those will not be in cleaned. Right? So how are we going to do that? Well, I'm going to start out with an index for the input, and I'm going to process each individual character in the input. So while raw input I is not equal to null, I'm going to do an I++. But more importantly, I'm going to check, and I'm going to make this all lowercase. So first off, I'll just deal with lowercase. So I'm going to say cleaned at I is equal to raw, or to lower raw input I. And I'm going to include CC type. So be clear as to what we're doing here. I'm walking through, I'm processing raw input, and I'm copying every single character in raw input into the same exact index in cleaned. And when I'm done, cleaned will have a lowercase version. Now I haven't dealt with spaces yet, but I'm just going to test one thing at a time. Oops. Let me just make sure that built. Looks like we might have a little problem here. We'll run it, ABA. It says no. All right, so let's make sure we've got this correct. Let's print out cleaned input. Just to make sure it is what we think it would be. Cleaned input has ABA and then a whole bunch of garbage in it. That's really kind of glad that we made that mistake here. What happens when you don't have a null character at the end of a C string? I told you that it would print out some garbage, and that's exactly what we're seeing here. If we look into Visual Studio, cleaned is a blank array. It's a completely blank array. It's C. If I walk through while raw input's not equal to the null character and just copy everything in, well, when raw input is the null character, I don't do anything, and I never copied it in. So one of the things that we'll need to do is to put cleaned at I is equal to the null character. So now let's give this a try. And now we got that as a palindrome. We can see the cleaned input has a lowercase. This is a really illustrative example up here. Notice you see that the original input up here. That's because this is actually just a complete buffer overflow, and we're printing out variables, the content of variables. In memory, my lowercase cleaned was at an address right next to my original raw input variable. And in fact, when cout went to print out this string, it printed out up until it hit a null character in memory. At every specific address, it didn't find null. This was some unprintable garbage kind of character data. Eventually, it blew right past my array. And if you went through and you counted this, you'd see there's 50 characters here. It went right into the next array in memory, and then that did have a null character at the end. That was what the user typed in. So this is a really, if you ever see something like this, you want to know exactly why that's happening. Okay, so the next thing we need to deal with is spaces. Now this is a little bit more tricky, because if raw input I happens to be a space, we don't want it to go into cleaned. If that's the case, cleaned might not necessarily be the same length as raw input. If I say A space BA, clean's only going to have 3 characters. So rather than always putting whatever's at raw input I into what cleaned I, what I'm going to have to do is I'm going to have to create another index. Int j equals 0. And j is going to represent the index where the next thing goes into the cleaned array. And that's not necessarily going to be the same thing as I. So what I'm going to do is I'm going to say if not is space, or let's say is space raw input I. If it's not a space, we're going to add it to cleaned. And we'll do j++. If it is a space, we're going to ignore it. We're not going to increment j. We'll still move on to the next thing in raw input, but we'll keep j where it is. And then at the end, we don't want to put cleaned I, we want to put cleaned j. So this is the source index, this is the destination index. If we run this now, put a bunch of spaces in, we can see the cleaned input is ABA as well. So this function simply cleans the input, and then we can ship the clean input into is palindrome. All right, so let's get some practice with C strings. Lab 11, I'm going to ask you to write a program that reads 2 specific strings from the user. And sorry, this should not say string class. We'll do that next. And I want you to determine whether the 2 strings are anagrams. So it's just kind of similar to palindromes. Anagrams are words that contain the same letters in any order. So 2 words are anagrams if they have the same number of letters and the same letters themselves, but they can be mixed up. They can be in any order. I'm going to give you can complete this lab any way you want, but I'm going to give you kind of a strong recommendation as to how to do this. The way I would approach this is to write a function. I do this in 2 steps, first off. Without worrying about multiple strings or anything like that, I'd write a single function called count characters. Count characters, that function's job is to accept a single C string, and a character to count how many times that character appears in that single C string. So count characters should accept 2 parameters, a string and a character. It should return an integer. Right? And you can use a regular while loop to go through that C string and find out and count how many times do you find that particular character. Now, count characters does not solve the problem of his anagrams. It doesn't have anything to do with anagrams, but it's going to be an enormously valuable tool for your program. So don't get ahead of yourself. Don't think that count characters needs to deal with two strings or somehow has to also think about anagrams. It's a tool. Develop it, write a little program, test it, make sure that you can type in a word, type in a character, and it'll print out how many times that character appears. But once you know that you have count characters working or count characters working, now turn your attention to anagrams. You can write a function that accepts two strings. If A and B, or strings A and B, if A and B aren't the same length, then there's no point in continuing. If they're not the same length, they're not anagrams. You don't have to call count characters or anything. Next step, if we want to deal with capitalization and spaces, you want to clean the input. So convert all of A and B to lowercase. Then the third step, and this is where count characters is going to come in handy. For each letter in A, remember that these strings are the same length, because if they're not the same length, they're not anagrams, and we're done from step one. For each letter in A, call count characters on A with that letter and B with the same letter you found in A, and see if the results match. What this is essentially doing is allowing you to go to each and every character in A and make sure it appears the same number of times in A as it does in B. And count characters will do that for you perfectly. You'll call count characters twice, once with A, once with B. If you make it through every single letter in A and they appeared in A the same number of times as they appeared in B, they are anagrams. So that would be the recommended approach for Lab 11.